Alright, so let's suppose that we're interested in finding a certain type of integrals such as x times e to the power of x squared dx. Now, how would we go about finding this? Because we actually have a product of two functions here. Well, there is a method called the method of substitution that tells you that if you have some function of x here, and the other function of x happens to be the derivative of one of the parts of that function, then you can make a substitution of variables such that the integral is reduced to one that you can actually integrate using the standard methods that we have learned so far. So let's try and find that such a relation in this integral. We have e to the power of x squared. So let's see what happens. What happens if you differentiate this power? We get 2x. Now, what is this similar to? Well, this is similar to x. The only difference is that we have that constant 2 at the front. So how can we manipulate this to make it look like that? Well, we can use the algebraic method, the algebraic technique that I told you in a previous video, where you can just put a 2 at the front there. And in order to balance that out, you put 1 over 2 outside the integral as a constant. And now you're going to have this e to the power of x squared dx. And if you notice, this is actually the exact same as this. We have just changed the way we have written the integral, but it is essentially the same function. So now that we have that relation, what can we do? Well, we can do something like this. We can say, let's say a new variable u is equal to x squared. And let's have du over dx. So let's differentiate this new variable with respect to x. That's going to give us 2x. All right, that's all good. Now, what can we do to this so that we have an expression for 2x times dx? Because we can rewrite this as integral of e to the power of x squared times 2x dx. Well, we can multiply both sides by dx, and that's going to lead to the following expression. Du is going to be equal to 2x times dx. So that means that this part of the integral is going to be du, and this part of it is going to become e to the power of u. So let's rewrite this integral as half of the integral of e to the power of u with respect to du. Can we integrate this? Well, yes, we can. We can use the standard methods we have learned in previous videos, and this is going to be equal to half of e to the power of u, because remember, there's just a 1 in front of the u here. So if we divide this by u, if we multiply that 2 by 1, that just stays the same, and we're going to add the constant at the end. So the final step in writing the solution to this integral here is to replace the x back into u. So this is going to be equal to half of the exponential function times x squared plus c. So how can we actually check that this is correct? Well, we can just differentiate it. So if we differentiate this, d over dx of the function half of e x squared, we're going to employ the chain rule. So this is going to be 2x times e to the power of x squared, and the c becomes 0. Now those two cancel out, and then we have the original expression that we were integrating in the first place. So yes, this is in fact the integral of that function. Now, there are certain things that we can do. It is not just about what we can do with these type of functions. We can also apply other types of substitution. So I'm going to show you a few more examples just so that you can get a better idea of how this method works. It is all about finding some relation between the two functions. So let's say we have the function sine x cosine of x dx. So how do we integrate this? Well, you can notice immediately that cosine is the derivative of sine. So we can write this as u equals to sine, such that the derivative du dx becomes cosine of x. And now we want to write an expression for this whole component here, so we can just multiply this side by dx, and that means that we're going to erase it, move it from here, such that this whole chunk of the integral becomes du, and this is just going to be u. So we can rewrite the integral as u times du, which we know is just going to be u to the power of 2 over 2 plus the constant c. And if we substitute sine of x back into here, that is going to give us sine square x over 2 plus c. And we can check that this is correct by differentiating this with respect to x. And we would in fact get back to this function here. Now what happens with an integral like this? X times the square root of x squared plus 1 dx. Well, we can notice that inside of this square root we have the expression x squared plus 1, and if we differentiate that we get to x. So let's write u equals to x squared plus 1, and here we're going to have du equals, I'm just going to put the dx on this side, this is going to be 2x dx. So this is almost the same as this portion of the integral, but the only difference is that we need that 2, so we're going to put a 2 in there, and to balance it out we're going to put 1 over 2 on the outside of the integral. So now we can rewrite the integral as half of the integral of 2x times dx, that's going to become du, and this expression here is going to become u, so this is going to be square root of u, which is the same as saying integral of u to the power of 1 over 2 du, and if we integrate this we're going to get 1 over 2 u to the power of 3 over 2, and we need to divide this expression by 3 over 2, so this is going to give us 3 and 2 here, so the 2's are going to cancel out, plus c, and immediately this is going to lead to the final expression, which is going to be by our substitution of this expression back into u, so that's going to be x squared plus 1 to the power of 3 over 2 over 3 plus c. So does this go back to the original function? Well, if we differentiate this using the chain rule, we know that this is going to come down, so that 3 is going to cancel out with that 3, so we're going to be left with a 2 on the denominator. And then if we differentiate the inside, we're going to have this function times 2x, so that 2 is going to go with that 2, and in the end we end up with the expression we had in the beginning. Now there's another type of substitution that you can make, which is called trigonometric substitution, and it simply means that we're going to be using trigonometric identities to find a better way to integrate something. So let's have the integral of tan of x with respect to dx. Now we don't know how to integrate tan yet, but what about the relationship between tan and sine and cos? Well, we know that tangent is equal to sine of x over cosine of x dx. And what do you notice about this expression? Well, one of them is the derivative of the other, but we need to be careful as to how we write that, because if we have, for example, u equals to sine, and then we have du equals to cosine of x dx, notice the issue we have here. Cosine of x is in the denominator, whereas the dx is on the numerator, so this expression wouldn't be useful in this case. What we need to do instead is have u equals to cosine of x, such that du is minus sine x dx, because sine x dx is on the numerator, so this is going to become du. And the only thing that we need to change is to multiply this by minus 1 here, and to balance it out we need to have a minus 1 on the outside as well, so these two cancel out. So what is this going to become? Well, this is going to be equal to minus du over u. So how do you integrate 1 over u? Well, remember that when we have this is the same as saying 1 to the power of minus 1. But the problem with this is that if we add 1 to the power and then divide by this, what are we going to get? We're going to get u to the power of 0 over 0, and this is undefined, so we really cannot have that. So instead what we're going to have is the integral of this is going to be natural log of u. And the reason for that is that if we differentiate this function, we know that we're going to get the derivative of the inside, which is in this case just 1, and we're going to divide that by the function itself. So this is why we're going to have this. So let's replace that in here. So finally our integral is going to be minus ln of u, and we usually use absolute value bars with natural logs that we have just integrated plus the constant c. So now all there is left to do is to replace u by cosine of x, which was the substitution that we made, so cosine of x plus c. And this is the integral of tan of x. That's how you derive it. So there are many other things that you can do with this, and there are a lot of trigonometric substitutions that become quite useful to perform this kind of integration. So you have to look for different hints on the integral and the function that you're integrating, such that you try to manipulate it and you can integrate it later on using these kinds of substitutions and so forth. Now in the next video I'm going to show you how to integrate functions that are actually products of two functions like this, using a method called integration by parts. So that's what we're going to cover in the next video.